Let's get started now that our cameras are working. Today we're going to continue multiprocessors, and we're going to hopefully tackle two important issues. One is memory ordering. Actually, they're both related to memory ordering. One is consistency, memory consistency, which is related to the ordering of all operations. And the second is cache coherence, which is related to the ordering of operations on a single cache block. That's the major difference between these two. As a result, they have totally different implications, but they're both related to getting things correct, programming multiprocessors correctly. But before that, you're already aware of this. There's a midterm coming up next week, April 23rd, which is next Wednesday. Right now, next Wednesday. It's in class. It's going to be similar to the first midterm in terms of spirit and questions, and except the content. Questions will not be the same. Closed book, closed notes. 2 cheat sheets are allowed. Basically, it's twice the same sheet as midterm 1, 2 times the same sheet. Scope is any topic we've covered so far in the course. That includes lectures, labs, homeworks, readings, review sessions, ... Okay? And as I've told you before, material after midterm 1 will have higher weight on the exam. That doesn't mean that we will not ask you anything from midterm 1 topics, because things build on each other, right? For example, MSHRs are very difficult to understand without understanding out-of-order execution, right? Hopefully you know what MSHRs are. I'll leave you with that. Okay, and I've already given you the suggestions last week, but the biggest suggestion is solve past midterms and finals on your own, in addition to obviously studying and internalizing the lecture material and studying hard. Check your solutions versus the online solutions, and you have many examples of exams, so you don't have any reason not to study for the exam, I think. Right, and the spring carnival is also over, so there's nothing that will block you now. Doing homework 7 is another thing that I would definitely recommend. Even though the homework 7 is not due before the exam, finish it. You don't need to submit it. If you want, submit it, but do it. And if you're actually looking for solutions for homework 7, it's really in the past exams, because the questions that are in homework 7 are actually coming from past exams. Okay? And do the readings that are required, including the reading for today, which is this paper. Even I did it yesterday, again, for the nth time. It's only 2 pages, actually. It's less than 2 pages if you count it's 1.5 pages by Leslie Lamport. It's about consistency. Well, sequential consistency. It's a paper that introduced what we will talk about today. Okay, any questions on the exam? Okay, well, remember we ended the lecture with something like this, difficulties in multiprocessing. And I told you that much of parallel computer architecture design and research is about 2 things. One is designing machines that overcome the sequential bottleneck and the parallel bottlenecks to achieve higher performance and efficiency. And we know what those bottlenecks are. Sequential bottleneck is denoted by Amdahl's law. Parallel bottlenecks in the parallel portion are threefolds, right? Synchronization, they're due to 3 things: synchronization, load imbalance, and resource contention. And the second part of parallel computer architecture is mainly about making programmers' life easier in writing correct and high-performance parallel programs. And these 2 are both requirements, correct and high performance. If you leave one, then it's really easy to do this. Right? You can get a program really high performance while sacrificing correctness, right? And vice versa. You can get a program really correct by sacrificing performance. The art is really doing both. So we're going to talk about actually both in the next few lectures. Today we're going to focus a lot on this, basically. How can we have the infrastructure in a multiprocessor that enables programmers' job to be easier to program these machines? This is the reading that I just showed you, Lamport's 1.5-page paper that talks about consistency. So we're going to talk about memory consistency. This introduced the idea of sequential consistency, but there are a lot of other consistency models that I will allude to today, but I'm not going to talk about. Basically, this is the focus of the first part of the course, memory ordering in multiprocessors. And we've seen this issue before, right? You have a bunch of operations, A, B, C, D. The key question is, in what order should the hardware execute these operations and report the results to the software? We've seen this issue in out-of-order execution very well, right? This is determined by the ISA. It's a contract between the programmer and the microarchitect. Microarchitect has to provide some order that's determined, specified by the ISA, and the programmer assumes that order, and they can write correct programs, hopefully in a sane way. And this order, preserving an expected order, simplifies the programmer's life. If there's no order of these operations, then it's going to be very difficult for the programmer to debug the program, as we've discussed, right? When we talk about precise exceptions, for example, the notion of precise state, it's all about the ordering of instructions. Von Neumann model makes it simple in a sequential ISA, because it says that the instruction order that you see is the same as the program order, and the hardware is strictly supposed to obey that order. You cannot execute an instruction before the previous instruction in the program order is complete. That's it, basically, right? So this simplifies programmers' life. This leads to ease of debugging, ease of state recovery, ease of exception handling, everything we talked about in the precise exceptions lecture. The downside is, this is a great example of programmer-microarchitect trade-off. Preserving an expected order usually makes the hardware designer's life difficult. And we've seen this when we talked about out-of-order execution, right? Actually, even in-order execution with multi-cycle operations, you need those structures that we've discussed to preserve precise exception semantics, reorder buffer, future file, history buffer. Those are all different structures that could potentially support this. Especially if the goal is to design a high-performance processor, these structures need to be relatively complicated. When we talked about load-store ordering, for example, load-store queues, the purpose of a load-store queue was to preserve order, but also to supply the data of out-of-order executed stores to later loads. And to both preserve order and to get the data, you needed to do complicated searches within this load-store queue. And this was a scalability bottleneck. It was one of the most complex part of the out-of-order execution engine, if you remember, right? If there was no ordering requirement between loads and stores, then you don't need this piece of logic. But then the programmer would go crazy, because how would you figure out which load is supposed to get data from which store, right? That'd be terrible. Okay. So in a single processor, the memory ordering is specified by the von Neumann model. We're assuming von Neumann model for single processors. And this is the sequential order. Hardware executes, and we're going to focus on load stores. Von Neumann model is much stronger than loads and stores. But in shared memory multiprocessors, it's the loads and stores that are really visible to, potentially visible to other processors. An add, unless it actually operates on a memory location, is not visible. And we're going to assume that adds actually operate on registers. So hardware executes the load and store operations in the order specified by the sequential program, right? And out-of-order execution does not change the semantics. Remember, hardware retires or reports to software the results of the load and store operations in the order specified by the sequential program. That's the whole purpose of this load store queue. That's the whole purpose of the reorder buffer. And the advantage of this is big, because you can get architectural state that's precise within an execution. And architectural state, there are two advantages. One is you get precise exceptions, precise architectural state, which enables you to debug really efficiently and well. The second is architectural state is consistent across different runs of the program. When you repeat the program, you get the same bug, right? Hopefully, if there is a bug in your program. Unless there's something else that affects the bug, like you generate a random number and the bug gets triggered because of that randomness. But that's not related to the order of execution of operations. It's something related to something else. So it's easier to debug programs because of these two reasons. The disadvantage, again, the preserving order adds overhead to hardware, reduces performance. Actually, if you don't preserve order, you can retire instructions in any order, then you don't need to have another stage in the pipeline. It increases complexity and reduces scalability. But we tolerate that. In a dataflow processor is kind of the extreme, right? We've also talked about this in the dataflow processor. A memory operation executes when its operands are ready. Ordering is specified only by the data dependencies, which means that there's no single order that the programmer can count on. Two operations can be executed and retired in any order if they have no dependency. Now, the advantage of this, as we've seen in the data flow, you get lots of parallelism, right? You get high performance. In fact, irregular parallelism is, data flow was one of the best models to extract irregular parallelism out of programs. The disadvantage, now order can change across the runs of the same program. Right? Very hard to debug. You run the program once, you get some memory order. You run the program again, you get some totally different memory order, because the latency happens to be different because your cache contents were somehow different, right? Too bad. It's nothing related to this random number generation, right? It's purely related to the memory order. It's very hard to debug because the bug may not appear because the memory operations may execute in totally different order now. So we're going to see that this problem actually exists in a MIMD processor, which is a multiprocessor, in a similar way. Dataflow is the extreme. You have the single sequential processor and the dataflow processor. Dataflow, there's no order except for data dependency order. Sequential processor, there's a perfect order, very strict order. MIMD processor sits in between somewhere. And MIMD processor is what we're talking about, multiprocessors, right? In this case, each processor's memory operations are in sequential order because we are going to assume the one Neumann model for each processor. And they respect, with respect to the thread running on that processor, obviously. But the operations of different threads have nothing to do with each other, at least so far, because multiple processors execute memory operations concurrently. Then the key question is, how does the memory see the order of operations from all processors? In other words, how does the programmer see the order of operations from all processors? And why is this important? What is the ordering of operations across different processors? If you don't impose any ordering across different processors, you can run into some problems, as I will show you. It's very similar to the problems that we see in the Dataflow processor. So why does this even matter? Let's take a look at that. There are three reasons. One is ease of debugging, the second is correctness, and the third is performance and overhead. Ease of debugging, it's nice to have the same execution order done at different times to have the same order of execution, right? This is kind of, well, I shouldn't say order or there. If you have a program that you're executing, if you execute it multiple times, you would like to see the same order of execution every time, right? This leads to repeatability. As a result, you can debug the program much more easily. You would like to do this for the same program at multiple times. The second is correctness. This is actually bigger than the correctness issue because we're going to see that consistency doesn't necessarily satisfy this debugging problem. We're going to get back to it. The second is correctness. And the key question here is, can we have incorrect execution if the order of memory operations is different from the point of view of different processors? Meaning that the order can change depending on the processor. And I'll give you the answer here. It's going to be yes. So we're going to try to avoid that incorrect execution. And the last thing is performance and overhead. If you actually enforce a strict sequential order, you can make life harder for the hardware designer in implementing some performance enhancements techniques like out-of-order execution and caches. Right? Especially in a multiprocessor, if you actually, let's say, enforce a strict order of operations somehow. Let's say you magically determine the global order of operations and you enforce that order. Now you're actually really serializing some things, right? Whereas the beauty of multiprocessing was, oh, everybody can execute their operations in parallel and you get lots of parallels. But we're going to have to do that so that we can achieve some balance between correctness and performance. So we're going to tackle this issue first. When could order affect correctness? And the key place where order affects correctness is when you're actually sharing some data. If you don't share any data between the processors and they're operating on totally independent things and they're never communicating with each other, you might as well not have any order, right? You might want to have some order just for ease of debugging perhaps, but it's not as important because the order of operations on data is not important to begin with, right? So semantically, the order of operations should be important. So let's take a look at protecting shared data. And I'm going to give you an example from this. If you have shared data, threads should not be allowed to update shared data concurrently at the same time, right? And when one is updating, the other should not be reading it, perhaps. Once all of the updates are done, then you should be able to, somebody else should be reading it. This is for correctness purposes. To enable this, accesses to shared data are encapsulated inside critical sections. We talked about this briefly last time. Basically, you have a critical section. Only one processor can execute it. The way it's satisfied is this critical section is protected via synchronization constructs. For example, locks, semaphores, condition variables. Are you guys familiar with this? Yes. Everybody? Yes. Especially if you've taken, well, 213 covers some of this, right? But if you've taken operating systems, you've gone to the guts of probably locks, semaphores, and condition variables. And if you haven't taken operating systems, I would definitely encourage you to do that because that shows you how actually real systems are designed. Basically, well, the easiest way to look at it is you have a lock and you have a critical section inside it. You do some operations and you unlock. And only one processor can hold the lock. That way you protect accesses to shared data, updates to shared data. I've already said that. This is the mutual exclusion principle. The key is, if you want to guarantee correctness, a multiprocessor should provide the correct execution of these synchronization primitives to enable the programmer to protect shared data. Right? If the multiprocessor does not enable the correct execution of these synchronization primitives, if the multiprocessor somehow leads to two processors being in the critical section at the same time, even though a programmer did the exact right thing, then there's a problem. Right? The programmer programs correctly, they use the correct synchronization constructs, but the hardware somehow allows two processors to go into the critical section at the same time. Too bad. Then the programmer cannot rely on anything and cannot program this processor. So supporting mutual exclusion, basically programmer needs to make sure mutual exclusion is correctly implemented. That's not the subject of this. That's a whole other subject, right? How do you actually ensure that the programmers can correctly implement synchronization or mutual exclusion? And this is actually one of the toughest part of real parallel programming. If you want to design a high performance program and get it correct, you want to have these synchronization constructs to protect as little as possible. As you reduce the size of your critical section, it becomes harder for the programmer to reason about which data is shared and which data should be protected and which data should not be protected, and which code section should be protected and which code section should not be protected. As a result, you get into these bugs. But that's not the subject of this. I'm going to assume that for now. Well, this is an important topic. So if you actually want to learn about at least some of the basics of this is a fundamental paper by Edgar Dijkstra, that was written in 1965, actually, that talks about cooperating sequential processes, how they actually synchronize between different sequential processes. And there's an algorithm called Decker's algorithm for mutual exclusion that guarantees mutual exclusion. I'm going to use a very simplified version of that, not the exact version of that, to demonstrate whether the hardware can support mutual exclusion correctly, even if the programmer implements everything correctly. But this is actually something that I would definitely recommend if you're interested in this. Perhaps do the reading after this course, though. It's going to be long. Okay. So a programmer relies on hardware primitives to support correct synchronization. Assume that they correctly implemented synchronization. If the hardware primitives are not correct, then the programmer's life is tough. Right? Or unpredictable. That's another thing. If the hardware primitives are correct but not easy to reason about, the programmer's life is still tough. So I'm going to show you these two different things. Let's first take a look at whether the hardware primitives can be correct or cannot be correct. I guess I'll repeat this somewhere here because I'm going to go into slides. So this is one very, very simplified version of Decker's algorithm. I wouldn't even want to call it Decker's algorithm. It's really similar to what you have in your reading, 1.5 page reading from Lamport. But we have two processors, processor 1 and processor 2, and they're actually accessing they're synchronizing for this critical section. And I'm not showing you everything over here that makes it required to get this correct. Actually, if you just look at this is not correct. There should be some things over here to ensure that this is correct. Basically, you have two flags, flag 1 and flag 2. Processor 1 initially sets flag 1 to 0. And before entering the critical section, it says flag 1 to 1, saying that it's going to enter the critical section. And then it checks flag 2. Flag 2, if flag 2 is set, that means processor 2 is in the critical section. Right? Then it shouldn't enter the critical section. Right? If flag 2 is not set, then the processor 1 can enter the critical section. And later on, it sets flag 1 to 0 before exiting the critical section. And this else over here is executed if flag 2 is set, which means that processor 2 is in the critical section. Then processor 1 should not enter the critical section and retry somehow. So that's the part I don't show over here. But this is the part that's really needed to guarantee correctness from the programmer's point of view. But it's really irrelevant to the discussion that I'm going to have now. And processor 2 does the same thing, except it sets flag 2 before entering the critical section and checks flag 1. It sets flag 2 and then checks flag 1 before entering the critical section. If it's not set, then it can enter the critical section. Okay? So critical section means that only one processor has to be in this, can be in this critical section at any given time, not both. Right? At most, one processor should be in that critical section. Let me put this over here so that we can take a look at it. Basically, processor 1 does this, sets F1 to 1, and then the second operation is this. If F1 is not equal to 0, I guess, right? Yeah, equals 0. That's right. No, F2. See, it's really easy to get parallel programs wrong. And then you do the critical section. And then I'm not going to show the rest. And then processor 2 does this. X sets F2 equal to 1, and then checks if F1 is equal to 0. Then it enters the critical section, does some things, and then gets out. Okay. So assume that P1 is in the critical section first, over here. Intuitively, it must have executed A, right? Because we're assuming one Neumann model over here. Which means that F1 must be 1, because A happens before B, right? B is this if F2 equals 0. Which means that P2 should not enter the critical section, right? That's why this works. It satisfies the simple happen before relationship. Okay? The key question is, can the two processors be in the critical section at the same time, given that they both obey the one Neumann model? Yes, you're saying? Okay, so you've already figured it out. And the answer is yes, as you say. And I'm going to give you one example of this. There are many, many reasons why they could be. If this is the only assumption, both processors obey the one Neumann model, it could be yes. There you go. And one example is this, basically. You have P1, P2, and there's some interconnection network over here. And let's assume you have some memory that's distributed this way. And F2 is in this memory location, and F1 is in this memory location. And so happens that F2 and F1, F2 is closer to P1, and F1 is closer to P2. So it takes longer for P2 to get to F2, and longer for P1 to get to F1. Let's assume at time 0, processor 1 executes A, which is this statement. It sets F1 to 1. And this A is sent to memory. And it'll take a long time to complete. But processor 1 assumes that F1 is complete. This processor assumes that this is done. Right? And then it moves on to the next statement. At the same time, P2 executes X, which is this statement, and sends F2 all the way to memory. F2 equals 1, this update, this store to memory, and assumes that it's complete. Basically, the store to F2 is complete from processor 2's point of view. So at the end of time step 1, I guess, or 0, both processors have executed this, but the memory operations are not complete. The operations are not visible yet to the other processors, right? This is the same thing repeated over here. At the time step 1, P1 executes B, which is this statement. I guess I should put P1 and P2 over here. This statement, which it checks if F2 equals to 0. So it starts a load to F2, right? F2 is not anywhere in the registers, it's in memory. And remember, F2 is somewhere over here. That's close to processor 1. And F1 is somewhere over here in the memory that's closest to processor 2. Basically, at time step 1, processor 1 starts a load to F2. Okay? And this operation is sent to memory, this load operation. At the same time, processor 2 executes Y, basically starts a load for F1, and the operation is sent to memory. Now, memory, because F1 is farther from processor 1, this store to F1 takes longer than this load to F2. So memory returns F2 earlier. Right? Memory sends back F2 to P1 at time 50, let's say, 50 cycles later. This load to F2 is complete. And initially assume that, I guess, F2 is 0 and F1 is 0 because they were set much long ago. Okay? Make sense? So basically, at time 50, memory sends back F2 to processor 1, which is 0. At the same time, memory sends back F1 to processor 2, which is also 0. Now both processors got 0. So they can both enter the critical section, right? It's beautiful. Because hardware really didn't guarantee anything other than the one Neumann model. Well, later, they both went to the critical section. They can execute the critical section. And later, memory responds to the store. Memory completes F1 equals to 1 because it receives that request much later because there's some interconnection network. And this load happens much earlier than the store reaches its destination. Much later, F1 becomes 1. And much later, F2 also becomes 1 because the stores take a long time to execute because they get delayed. But it's too late because these processes have already checked the condition variables. Make sense? So that's why you get incorrect execution here. And this is pretty fundamental, and this is a very simple example, actually. There are much more complicated examples that you can come up with. So what happened here? Let's take a look at this. Processor 1's view of memory operations. It basically, the problem is you violate the intuition of happened before. And that's almost always a problem whenever you program distributed systems. Whenever you program distributed systems, this happened before relation should not be violated, then you get into consistency issues. That's why when I have my Gmail open in 2 places, they're not consistent because somebody violated that happened before relationship. So in this setting, P1, when it executed these operations, its view of memory operations was like this. It saw A first, it saw B next, and then much later the store became visible to P1. Maybe it tests F2 much later. At that point, it can see F2 is equal to 1. So if you think about it, it basically saw X much later than AB. So the order of operations was ABX from P1's point of view. P2's point of view, X was executed first because F2 equals 1 completed, even though it was not visible to P1. And then it executed Y. And much, much later, at time 100 perhaps, and after that, this A, the processor's V1 setting of F1 became visible to processor 2. And if you look at this order, this is ABX, and this is XYA. For processor 1, A appeared to happen before X, whereas it's exactly the opposite for processor 2. X appeared to happen before A. Now you have a violation, right? You cannot have both at the same time. And that's the problem. Both processors have to see the same order because this is not intuitive, right? It cannot happen that you can have these 2 different views of orders. Okay? So how can we solve the problem? Basically, now that you know the problem, you have to somehow ensure that this happened before relationship is guaranteed, which means that both processors have to have the same global order. And that's the idea of sequential consistency in this 1.5-page paper that you're supposed to read. Basically, all processors should see the same order of operations to memory. In other words, all memory operations happen in an order called the global total order that is consistent across all processors. If you guarantee that, you won't run into this problem. The assumption is that with this global order, each processor's operations appear in sequential order with respect to its own operations. So you still follow the von Neumann model. Von Neumann model is not broken, right? Each processor still has in-order operations, but there's a single total global order across all of those load store operations. And this is actually described crisply with 2 principles in this paper. Basically, a multiprocessor system is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order. So there's no single global total order. There could be many, many global total orders. Right? It could be A, B, X, Y, for example. Or it could be A, X, B, Y. Or it could be X, Y, A, B. Those are all sequentially consistent orders, right? As long as all of the processors see that same order. And the second one is von Neumann model based. The operations of each individual processor appear in the sequence in the order specified by its program. So this is really a memory ordering model or a memory model. It's specified by the ISA. And this is actually a mess. This has been a mess in many architectures for a long time because this is actually hard to reason about. Sequential consistency is easy to reason about, but if you want to get more performance, as we will discuss later, people have defined different models. Okay, basically what's the abstraction of the programmer? If you think about this, this provides an abstraction to the programmer that looks like this. Memory is a switch that services one load or store at a time from any processor, and no more than one load. All processors see the currently serviced load or store at the same time, and each processor's operations are serviced in program order. If you satisfy this, then this is sequential consistency. Right. You can think about this a little bit. So as a result, you get many potentially correct global orders, and they're all sequentially consistent. And I think I've enumerated all of them here. ABXY, AXBY, AXYB, XABY, and XAYB, and XYAB. Make sense? Anything else should violate sequential consistency. And which order is observed depends on the implementation and dynamic latencies. Depends on the interleaving, when this processor executes XY. It's very hard to actually enforce that the processor should execute XY, AB, only one global order, right? You can imagine that it's really tough. Then you need to really control all of the processors, which means that you lose a lot of parallelism. Okay, so what are the corollaries of this? First, within the same execution, all processors see the same global order of operations to memory. There is no correctness issue that we've seen before. This satisfies the happened before intuition. The second corollary, unfortunately, across different executions, different global orders can be observed, and each of them are sequentially consistent. As a result, the debugging is still difficult, right? Because order changes across runs. You run your program once, you get some order. You run your program again, you get some other order. Now, if you had a bug in the first run because of that ordering, you will not see that bug. You'll potentially not see that bug in the second run. This is very similar to the Dataflow processor, except it's a little bit limited. So we have not solved the debugging issue. Debugging issue is actually harder to solve. How do you guarantee that when you run your program, let's assume that you're debugging, how do you guarantee that in the next run you'll get exactly the same order? And people have proposed different methods for this. One idea is, for example, recording the order in the first run, and the second run ensuring that the same order happens. This is acceptable when you're debugging, for example, right? You write your parallel program, and you have some infrastructure. Your compiler, for example, records when you're running the program. Well, the compilation infrastructure, not the compiler itself. But you need to have some additional support in your program to actually record the order, and probably from the hardware as well. And then the next time you run the program, that order is enforced by the hardware. If you do that, then you can solve the debugging issue. I'm not going to talk about how you can do that. There's a lot of overhead associated with this to do that. And if you want to actually observe the same order in production runs, then this actually leads to a lot of overhead. You don't want to do that. You were going to ask that? Yeah. So that's why this doesn't happen in production runs. Even in debugging runs, a lot of people don't use this. But you would like to really have something like this to make debugging easier in multiprocessors. But at least we've eliminated the correctness issue, which is the first issue. Because if you don't get it correct, you don't care if you can debug it, right? Okay. So there are several issues with sequential consistency. It's really a nice abstraction for programming because it's really simple. But there are two issues. One is order requirements can be too conservative, perhaps, right? Maybe you don't have this. You shouldn't really have the strict ordering requirements across all of the loads and stores. Maybe a total global order is not good. As a result of this limits the aggressiveness of performance enhancement techniques. Well, I've already asked you that. I've already given you the answer, I think. Do we really need a global order across all operations and all processors? No. You have a better idea?
Well, only when you need to do that.
Exactly. Yes. Exactly. And that's the idea of weak consistency. You don't really, most of the time the processors don't communicate with each other, right? Only when you need to synchronize access shared data, maybe that's when you enforce the global order, enforce some order. It's not a global order anymore, it's a partial order now, right? Across all of the memory operations. Actually, there's a less strict, but not as strict model, which is maybe you need a global order only across all of the stores. Right? This is actually called the total store order model. And x86, for example, the processors that you use today, most of them, use a model like this. It's called the total store order. It's a little bit more complicated than that, but you can take a look at it. There's actually other models that are called unique store order model. Because if you think about it, loads, as long as you guarantee stores are the ones that really update memory locations. As long as everybody sees the stores in the same order, maybe it doesn't matter. Right? And this is the even more relaxed model. How about enforcing a global order only at the boundaries of synchronization? Only when you actually need to synchronize between processors, those operations are ordered. And that's the idea of the relaxed memory models. For example, acquire-release consistency model. You could think of having operations that looks like this. Before the critical section, you have acquire. After the critical section, you have release. And then you have another acquire here, and then another release here. And basically everything, all of these acquires and releases can be ordered with respect to each other. and everything else that are outside the acquire and releases, you don't care about the order, right? As long as all of the operations before the acquire are finished before acquire is complete, and you have a good order within these, and none of the operations after the release have started. Okay, I'm not going to go into detail, but there's a lot of research as well as models that have been proposed for this. There are two performance enhanced techniques that could make implementation of sequential consistency difficult. Actually, we're going to get back to this in a little bit. One is out-of-order execution. So out-of-order execution inherently violates some of this order, right? Loads happen out of order with respect to each other and with respect to the independent stores. This makes it difficult for all processors to see the same global order of all memory operations, right? Of course, you can fix this problem by redoing just for ordering, re-executing the load when it's retired, right? When it's about to retire. You can re-execute the load and re-execute the store just before it's retired, such that you have a single order. But then that adds overhead, if you think about it. Caching is another one. If a memory location is actually present in a cache and potentially present in multiple places, the cache prevents the effect of a store to be seen by other processors, right? How do you ensure that other processors see the effect of a store? Well, if you've cached it, they won't see the store, and they won't see the order. As a result, this also makes it difficult for all processors to see the same global order of all memory operations. Now you can overcome this. Whenever you do a store to a cache, you actually broadcast and say, oh, I'm doing a store to this memory location. Now everybody sees that you've done it, but then it kind of reduces the benefit of caching because you're actually using bus bandwidth to do this broadcast. So these are two things that make implementation of sequential consistency difficult. It doesn't mean that you cannot do it, right? You can guarantee that, but you need to add some overhead, hardware complexity to do that. As a result, people have proposed weaker memory consistency models by realizing that the ordering of operations is important when the order affects operations on shared data. Because that was the reason why we introduced ordering to begin with. Which means that when processors need to synchronize to execute a program region, that's why you want to preserve the order. This is the idea of weak consistency. And it may be difficult to do because the idea is programmer specifies regions in which memory operations do not need to be ordered. Right? And what are those regions? Whenever you're not synchronizing. And one example in modern ISAs is you have these memory fence instructions to delineate those regions. So actually, acquire release is one example, but you can have a memory fence over here. Memory fence means that you've got to finish all of these operations before the memory fence executes, and nothing else before the memory. Nothing that actually comes after the program, after the memory fence in the program should be executed at that time. So it's really a fence that guarantees precise memory states at this point. And what does it mean for all operations before this to execute? All operations before this should be visible to every other processor at that point in time. And no operation after that should be visible to any other processor after that point in time. Okay. Basically, all memory operations before a fence must complete before the fence is executed. And all memory operations after the fence must wait for the fence to complete. And fences complete in program order. Which means that you can keep inserting these memory fences into your program just to ensure that all operations happen in strict order. Just for those cases where you need it. Right? Make sense? And all synchronization operations act like a fence. That's what I said over here. Okay? Of course, the downside of this is now the programmer needs to distinguish between fence loads and non-fence loads, right? Non-fence stores and non-fence stores. You cannot just have loads and stores and forget about everything, which is what sequential consistency provides. It's beautiful. The programmer needs to say, oh, they need to think now. Is this load or store operating on shared data? And not all the times the answer may be obvious to the programmer, especially the programmer doesn't know the guts of the program, right? That's why you can get into issues over here with relaxed consistency models. Okay, so, well, I guess I've given you the advantages and disadvantages. So what are the advantages and disadvantages of weaker consistency? First advantage is because there is no need to guarantee a very strict order of memory operations, you can have higher performance than stricter ordering because the hardware implementation of the auto-order execution and caching can be simpler. You don't need to preserve the order all the time. The disadvantage is there's more burden on the programmer. just as I told you. Or the software. Somebody needs to get these fences correct. If you forget a fence, you can be back to square one, right? Again, this is another example of the many examples that we've covered in this course of the programmer-microarchitect trade-off. Weak consistency is great for the microarchitect because it's easier to implement, easier to enforce. In fact, no consistency is great for the microarchitect, but it's terrible for the programmer. Whereas sequential consistency is great for the programmer. If you want to actually take a look at some related questions, there is a nice question on last year's exam, last year's final, that I just want to point you to here. Okay, any questions? I'm not going to go into more detail, but this topic can go on and on. There's still debates as to what should the programming, what kind of programming models support better consistency. What should be the consistency model that's good for the programmer? It's not clear what that answer is yet. Any questions? Okay, let's move on to another interesting issue, which is caused by caching in multiprocessors. So caching is actually complicated because it not only complicates the ordering of all operations, just as we discussed. What does that mean? A memory location can be present in multiple caches, and cache prevents the effect of a store or load to be seen by other processors. As a result, it makes it difficult for all processors to see the same global order for all memory operations. But it also complicates the ordering of operations on a single memory location as well. Why? Because a memory location, again, can be cached in multiple caches, and processors that have cached the same location need to have the correct value of that location. But caching makes it a little bit difficult in the presence of updates to that location. And this is the cache coherence problem that we will talk about. So just before we go into it, the memory consistency model that we talked about is about ordering of all operations across, as seen by processors, right? This all operations that are coming from all processors, regardless of the memory location, should have a single order. That's sequential consistency. Cache coherence is about operations on a single memory location, just one address. And it's about ordering those and ensuring that you get the correct value on that single address. Okay, so some of the readings. I guess I made this required now, but that's okay. As long as you know the MESI protocol, you don't need to do this reading. But that's a beautifully written paper that introduces the MESI protocol that we will talk about. And again, as I said in the last lecture, none of these are really required. This is for your benefit. But Lamport's 1.5 page paper is required. And if you want to learn more about cache coherence, this is actually a topic that has been developed for a long time. We're going to talk about directory-based cache coherence protocol, for example, which was introduced before the MESI protocol, and a bunch of other things. We're not going to talk about these bunch of other things. If you take 742, you'll go into the guts of these bunch of other things, which are actually pretty interesting. Okay, so we've been talking about the shared memory multiprocessors, and many parallel programs communicate through a shared memory. This means that whenever one processor writes to a memory location, the other processor should be aware of that write somehow because it may use that value, right? You could have something like this. Each read should receive the last value written by any processor. Right? This requires synchronization. What does last written mean, right? And caching complicates the problem because what if this location is cached at either end, right? Whenever this processor writes to this location, what if this cache is not aware of that? Right? Now you have a problem. Yes?
Are we doing anything with virtual memory?
Say it again?
Are we doing anything with virtual memory?
What do you mean? Anything with virtual memory?
Virtual memory map to the same spot.
Oh, yeah, that's right. Yeah, these are virtual addresses. They share the virtual address space, basically. That's what we're assuming. And that's what a shared memory multiprocessor or tightly coupled multiprocessor is. All processors see the same virtual address. Okay? Oh, same virtual address space, I should say. So, which means that this A is really a virtual address, as well as a physical address in this case. Okay? But if two different pages actually map to the same same physical address, you still need to guarantee this. Okay? So it's really stricter than virtual memory. It's really, I would say it's really independent of the virtual memory. As long as you have an address that's shared by two processors, regardless of however it's shared, you need to guarantee this cache coherence. Okay? Okay, so let's take a look at Basically, the basic question is, if multiple processors cache the same block, how do they ensure they all see a consistent state? Again, this is about the single block. And we're going to look at block X. Initial value is 1,000. Let's say this processor 2, this is the cache of each processor. This processor 2 loads X into R2. The memory location gets cached in this cache. Later, this processor 1 also loads X into R2. The memory location gets cached in this cache. Now you have the same value. Later, this processor writes to this memory location, makes it 2,000. And when this processor executes a load from the same location, it should really not load 1,000, right? But 1,000 is cached in this location. Then you have a problem. So cache coherence is about ensuring that this processor does not load 1,000 but loads 2,000. Okay. So whose responsibility is this? That's the first question. Again, this is a programmer microarchitect trade-off. Who should guarantee this? You can say, oh, hardware is not going to guarantee anything. Let the programmer deal with this. Well, that's very tough, right? Because hardware is caching things underneath. And if the hardware doesn't help the programmer somehow, then it's very tough for the programmer to even reason about what's going on here. Right? Because caching is automatic, right? Caches are not visible. So you could punt the problem to the programmer. Can the programmer ensure coherence if caches are invisible to the software? That's very tough. Well, actually, it's doable, except with a lot of overhead, right? For example, you could do coherence, software-based coherence at the page level. You can share pages, and you can say, these pages can be cached, but except when I'm writing to this page, I'm going to flush those pages from all of the other caches. Does that make sense? Basically, you can have a protection bit set with the page, and whenever a process or program or thread is writing to that page, it basically triggers an action such that all of the other caches are flushed, and this process is the only process that owns permissions to that page, write permissions to that page. It writes to that page, and after that, it resets that bit such that everybody else can load that page. You can imagine that this has a lot of overhead, right? This is page-based protection and coherence. You don't want to do that. You could actually come up with other ideas, potentially. For example, what if the fine-grained ideas? What if the ISA provided cache flush instruction at a finer grain? Actually, this is something that doesn't work. Let's say flush local A. This flushes or invalidates the cache block containing address A from the processor's local cache. Well, this is not very useful, right? Because some other processor is writing to a processor's cache. You would like to, in that case, get rid of that location from your cache, right? Because you don't want to load the value that was cached on your end. But you cannot predict which processor is writing when another processor will write to that location. So this doesn't work. This is getting closer to a solution, flush global A. Basically, whenever you do a write, you execute this instruction. And the purpose of this instruction is to flush or invalidate the cache block containing address A from all other processors' caches. Now this may not be bad, right? Whenever the programmer says, oh, store to this location, also before that, it says it executes a flush global A instruction. Now this is getting similar to support for hardware cache coherence we're going to cover. The downside of this is if the programmer needs to do this, you need to somehow guarantee atomicity, right? If the programmer says flush global A, and everything gets flushed from all of the other caches, and before the store actually happens, some other processor loads that location again into the cache, well, you don't want that, right? So there are race conditions associated with it. If you have an instruction like this, you need to ensure that the store also happens at the same time, such that no other processor loads that location before this processor writes to it. So this is hard to do. But if you actually enable that atomicity, then it's going to be very similar to what we're going to be discussing. Or you can have flush cache instruction. Flush invalidate all blocks in cache X, right? Or maybe all caches. Now this is an even stricter, even more higher overhead solution. So these actually do not work if all you have is these instructions and you add these before the stores in your program. None of these work because you can get into race conditions again, as I said. Some other processor after the flush all caches instruction can load that location, and you can get inconsistent results. So the solution is really hardware because this simplifies software's job. And again, higher level solutions actually exist in the software, but they have a lot of overhead. And one idea is hardware automatically invalidates all other copies of block A when a processor writes to it. Right? This is going to have very similar hardware support to flush global, but hardware automatically does it. The programmer doesn't need to deal with it. And that's the simplest protocol that we will start with. You have caches that snoop or observe each other's write and read operations. If a processor writes to a block, all other caches invalidate it. Invalidate that block. Okay? Actually, I don't like this. The way it's phrased over here. All others invalidate the block. It should be, right? Okay, that's better. There you go. Okay. And this is a simple protocol. Let's take a look at this briefly. We're going to see more complicated ones, and you're going to implement a more complicated one, actually. So each block in a cache has two states, basically. And let's assume you have a write-through, no-write allocate cache. It can be valid or invalid. And there are actions of the local processor on the cache block. The local processor can read the cache block, processor read, or write to the cache block, processor write. And cache broadcasts on the bus. Assume a single bus that's broadcast, that can broadcast across all processors, that's visible to all processors. Cache broadcasts these actions on the block. Bus read, bus write for a block. So if a processor does a read to a block, it's broadcast on the bus. Let's take a look at the state diagram. Basically, you have initially you have an invalid block. If a processor reads that block, what happens is it goes into the valid state. Well, after loading the cache block, it's a bus read is sent on the bus. So everybody sees that the processor is reading this cache block. If a processor writes to that cache block, you send a bus write signal, and you stay in the invalid state because it's a write-through cache. We're going to see write-back caches later. Now, if you're in the valid state, this is the most important part. If you're in the valid state, if the processor receives a bus write signal on the bus, this means that somebody else is writing to this block. Then the processor the cache basically invalidates the block. That's the idea. Anytime you see someone else writing to a block, we invalidate the block. It's a very, very simple protocol. Right? It requires that everybody see every cache see every other cache's writes and reads. In this case, especially writes. Okay? So we're going to see more complicated protocols. But let's take a look at non-solutions to cache coherence first. I would argue that no hardware-based cache coherence is a non-solution to cache coherence because it's very expensive. Keeping caches coherent is software's responsibility in this case. It's beautiful because it makes microarchitects' life easier, but makes the average programmer's life much, much harder now. Now, do you need to worry about hardware caches to maintain program correctness? As if you didn't have enough things to worry about to make your programs correct. Right? This was actually one example that I like to give is, you know about IBM's cell processor? This was used in PlayStation. It's a very tough to program machine because it doesn't have hardware-based cache coherence. The programmer needs to deal with all of these processors operating on different data. And it needs to ensure in software that the scratchpad memories are kept coherent. Well, that's true for many other processors also, actually, that do not have cache coherence. But there aren't many modern ones that are exposed to so many programmers. So the other downside is overhead. You have overhead in ensuring coherence in software. If, for example, if you do page-based coherence, as I described, you need to do page protection, and you need to flush all of the other pages. The second non-solution is have only shared caches, right? This happens only when you have private caches to processors. What if all your caches are just shared? Well, that's great, right? Then you eliminate coherence. There's no need for coherence if caches are shared because memory address doesn't get replicated across different caches. You have a single cache. The problem is it's very difficult to design this, right? Shared cache becomes the bandwidth bottleneck and latency bottleneck also. Right? And it's very hard to design a scalable system with low latency cache access this way. So we're not going to cover that. So we'd like to guarantee that all processors see a consistent value for the same memory location to guarantee coherence. This is basically consistent updates. Writes to location A by processor 0 should be seen by processor 1 eventually, and writes to A should appear in some order. There are two guarantees that you really need from a coherence protocol. First, write propagation. The coherence protocol needs to guarantee that updates will propagate to other caches. And the second is write serialization. You need to have consistent global order seen by all processors. Again, you cannot violate. One processor cannot see updates in different order to a memory location than another processor. Otherwise, you can get the wrong value, right? You can think of this as sequential consistency for a single memory location, not for all locations. Basically, you need a global point of serialization for the store ordering. Basically, this is write serialization requires ordering, and you need to have a global point of serialization. And the protocol that I described, the bus that's shared across all processors, was a global point. But we will see some other protocols that are more scalable that still have that global point. Okay. Let me see when I should take a break. I guess we can keep going for a while. So the basic idea is a processor or a cache, I'm going to use them interchangeably, broadcasts its write or update to a memory location to all other processors. Another cache that has a location either updates or invalidates its local copy. So now I'm introducing some other option, an update. Before I talked about an invalidation-based protocol, right? So you have this trade-off. When a processor broadcasts a bus write, saying that it's writing to this location, does it also broadcast the data such that all other processors that have that block update the data? Or does it just broadcast and invalidate, saying everybody who has this block should just invalidate it? So this is a fundamental trade-off in all coherence protocols. This is called an update protocol. If you push an update to all copies, it's called an invalidate protocol if you ensure that there's only one copy and then update the data. So how does it work? On a read, if local copy is invalid, the processor puts out a request. If another node has a copy, it returns it. Otherwise, the memory does. Right? On a write, this is where it matters. The processor reads the block into the cache just as before. In an update protocol, it writes to the block and simultaneously broadcasts the written data and an address to all of the other processors. And the ones that have that block update the data in their caches if the block is present. In an invalidate protocol, the processor writes to the block and simultaneously broadcasts invalidation of address to the sharers, and all other nodes invalidate the block if they have the block in their caches. Okay, it's pretty simple. But which one do you want? Right? Because they both have trade-offs, right? Which one would you pick if you were designing a cache coherence protocol? Yes?
Could you do a little bit of both?
A little bit of both. That's always a good answer, right? It depends is a good answer.
So
Yes.
if you have like a lot of processes, right, and then you have this block
Mhm.
that's present in a lot of the caches,
Mhm.
it means that it's clearly going to be utilized a lot. So you probably want to send the data so you don't
Mhm.
have everybody requesting that same thing from memory all over.
Again, yes. Maybe.
Yeah, but if you have it only used in like a few processors, you could just kind of send it out and invalidate it so as not to use as much of the bus.
Yeah. So issue is actually not how many processors cache this block, but issue is how many processors are going to write to this block or read this block again after the update. So you're onto something definitely, but it's really about after you do the write, would these other processors require the data again? So how this is called sharing behavior. How do you actually share? How are you actually sharing this data? For example, you would like this if you have an update protocol. If you have a constant sharer set, which means constant set of processors that are sharing, and you don't have a lot of updates, you avoid the cost of invalidation and reacquire, right? It's better to just push the data to other processors, and the other processors can use this data and can go on. Whereas, if the other processors are not going to use this data, then you don't want to update the data to begin with, right? Update protocol is bad if the data is rewritten without intervening reads by other cores. For example, you have this processor that keeps updating a cache block, and there are 10 other processors that have the same cache block. This processor keeps updating, keeps writing to this cache block. If you have an update protocol, it's bad because all of those updates will be updating all of the other cache blocks, so you cause a lot of traffic on your bus or interconnect. In that case, it's better to have an invalidate protocol. Whenever you do the write, you invalidate all of the other blocks, done, and you keep doing the write to your cache block. Okay? So it really depends on the access behavior of the processors. The other downside with the update protocol is now you have kind of like a write-through cache policy, right? You're really writing through your cache. And your bus can become bottleneck if you're always updating. Invalidation is good because after an invalidation is broadcast, the core can have exclusive access rights to that particular block. Right? Because if the invalidation is implemented correctly, the core at that point knows that it has the only copy. I can keep writing to that block without notifying anyone. That's the beauty of exclusive access. That's what exclusive access means. A processor can modify the cache block without notifying anyone. That way you save a lot of bandwidth, right? You don't need to send invalidations. Well, definitely not updates, but also no invalidations to any other core, any other processor. And only cores that keep reading after each write retain a copy in this case, right? So you don't send the data to other processors. So in this case, if you update the processors, some processors may get the data, but they may never use that data again. They may never access that address again. So invalidation is more efficient in the sense that the processors that need the data will request it again. Okay? The problem with invalidation is if you have lots of writes happening, this can lead to ping-ponging. Basically, you can have many, many invalidations. Right? So for example, think about this case where this processor 1 is writing to this cache block, and then this processor 2 is reading this cache block, and then later this processor is writing to this cache block, and this processor is reading to this cache block, and then ... And this happens actually a lot with locks, if you have lock contention. What would happen with an invalidate protocol is this processor would write to the block and invalidate the cache block here. And when this processor get the cache block again, so it will put out a request. And then later when this writes to the block will be invalidated from all caches again. And then when this processor reads the block, it will need to send a request and get the block. Whereas if you figured out that this was going on, whenever this processor actually wrote to the block, you would update the data and all of the other processors are sharing it, such that the next time this processor doesn't need to send a request to get the data. Right. So this, whenever you have lock contention, and this happens usually with locks, because you may actually have contention for a lock. This processor is writing to the lock, this processor is reading from the lock. This leads to something called ping-ponging. Ping-ponging is the idea of a cache block that's being that was actually in one cache, that it gets invalidated, and then that gets re-requested. Right? You basically have the cache block traveling across caches. Okay? And if that happens a lot, then you have lots of invalidations and reacquires, lots of requests on the bus. Okay. Let me introduce two cache coherence methods, and then we're going to take a break, and then we'll continue after that. Basically, two cache coherence methods differ in how we ensure that proper caches are updated. We've already seen the Snoopy bus, actually. Snoopy bus it's called the Snoopy bus. It's not the Snoopy dog, but basically, caches snoop each other's requests. Assume that you have a bus, which is a single point of serialization for all memory requests, and all of the caches, all of the processors, observe all of the other processors' actions on this bus. And for example, whenever processor 1 makes a read exclusive request for A on a bus, read exclusive means I'm going to write to this cache block, so give it to me in an exclusive manner, such that no one else has it. Processor 0 sees this and invalidates its own copy of A. Okay? The other is a directory-based protocol, which is actually older. You have a single point of serialization per block that is distributed among the nodes. So this is more scalable. In this case, it's more explicit. Here, it's kind of implicit. Basically, whenever a processor reads or writes to a block, everybody sees it. Here, a processor actually makes explicit request for a block, and there's a directory in some location that is accessible by all of the other processors. It tracks which caches have each block. And the directory coordinates these invalidation and updates. So the protocols can be similar, but how it's done can be different over here. For example, processor 1 can ask the directory for an exclusive copy, saying that, oh, I want this cache block, I'm going to write to it. So it sends a request to the directory, and then directory knows which caches actually contain that cache block. For example, directory knows that P0, some other processor, has this block modified in its cache. The processor, or present in its cache, the directory asks processor 0 to invalidate that block from its cache. It waits for an acknowledgement, and then responds to P1 saying that, P1, I know that none of the processors now have this cache block, so you can safely write to it. So there's more involved here. As you can see, this is probably more efficient in the sense that you don't go through this extra step of consulting the directory to figure out where the cache blocks are. In fact, here you don't even know where the cache blocks are. There's no central location that knows where the cache blocks are. Whereas in the directory-based scheme, there's a central location that knows where the cache blocks are cached. The upside of this is it's more efficient. You don't have this additional latency. The upside of this is it's probably more scalable, right? You don't need to have a bus in this case. You just need to have a directory that receives these requests. And you can distribute this directory because this kind of serialization happens per cache block. You don't need to have a single location that receives all of the requests for all cache blocks. Okay, so we're going to cover directory-based cache coherence after 5 minutes. You can think of some questions to ask, perhaps. Everybody's silent. So these were the two cache coherence methods, and we're going to look at both in more detail. Although the valid-invalid protocol, VI protocol that I called it earlier, with 2 states was one example of the Snoopy bus. Let's take a look at the directory-based cache coherence protocol. The idea here is you have a central, or at least logically central, directory that keeps track of where the copies of each cache block reside. And caches consult this directory to ensure coherence. It's a pretty simple idea. It's logically central because physically it doesn't need to be centralized, right? You can have a directory location for every possible block in the system. So it can be very distributed in that sense because you only need to guarantee serialization for a given block, not for all blocks at the same place. So an example mechanism, for each cache block in memory you can store p+1 bits in the directory. Let's say you have p processors. You have a directory that looks like this. Assume it's central in this case. For each cache block, you have p+1 bits. And the p bits indicate whether the block is present in the processor's caches. For processor 0, processor 1, ... processor, I guess, p-1. You can keep track of whether this block, this particular block, let's say block 0, is present in the caches. And the +1 bit indicates that you have actually one processor that has the block as exclusive. So if no processor has a block in the caches, this is all 0. This bit vector is all zeros, saying that block 0 is not present in any processor's cache. Make sense? If only, for example, processor 0 has it, and it's exclusive, meaning that exclusive rights were granted, processor 0 has the block, it's exclusive, and processor 0 can modify that block however it wants. Right? It can basically write to that block without telling anything to the directory, because the directory knows that processor 0 has that block in an exclusive manner. Now, if 2 processors, let's say processor 0 and processor 4, 0, 1, 2, 3, I cannot count. Processor 3 have the block, both caches cached in their caches. The block cannot be exclusive, obviously, because if one of them modifies it exclusively, the other one will have their own copy. The directory keeps track of it this way. Basically, 1 bit per processor that indicates, or cache. When I say processor and cache in this case, assume that they're the same. That indicates whether the block is in that cache. An exclusive bit indicates that a cache has the only copy of the block and can update it without notifying others. But in this case, they don't notify others because every access to a block goes through the directory, so without notifying the directory. So on a read, you set the cache's bit for that block. On a read to a block, you set that cache's bit for that block and arrange the supply of the data. The directory does this. On a write, the cache requests this block from the directory, sending a read exclusive request or write request, and the directory invalidates all caches that have the block and resets their bits. And the directory knows which caches have the block, right? Because it has a bit vector to keep track of that. And this exclusive bit, if a cache has exclusive access, it needs to record that exclusive access in its own tag directory, right? Tag store. There should be an exclusive bit associated with each block in each cache so that the cache can update the exclusive block silently, right? That's another thing that you have to have in the cache tag store. Otherwise, how would the cache know that it has this block in an exclusive state, or if the block is shared, right? Okay? So that's the idea. It's pretty simple, right? So let's take a look at an example of how this works. Basically, I guess you could follow this, right? This is a simple example. Let's say we have 4 processors. In that case, we have 4 + 1 bits for this particular block. And let's say we're considering block A over here. And I'm going to change this such that I have 1, 2, 3, 4 bits for processor 0, processor 1, processor 2, processor 3, and then exclusive bit. And then let's say this is block A. We're concerned about only one block here. Let's say initially no cache has this block. So you have all of these as 0 in the directory. And you have processors over here. Processor 0, processor 1, processor 2, processor 3. Processor 1 takes a read miss to block A. It sends a request to the directory saying, I want to read block A, right? Read A. Let's say. The directory checks, well, you're doing a read in this case. No cache has the block. No cache has the exclusive. So the directory can say, oh, processor 1, you can have the block. And directory sends a message to memory, getting the block and sending the block back to processor 1. There could be other ways of doing this, but this is the simplest way. Later, let's say processor 3 sends a read request to block A. It sends a request to the directory, read A. The directory checks, nobody has an exclusive, because processor 1, when it actually wanted the block, it didn't say, I'm going to write to this block, right? It said, I'm going to read this block. So directory didn't grant the block to be exclusive in that case. So the next processor, processor 3, sends a read request. In this case, the directory says, oh, processor 1 has the block, but it doesn't have an exclusive, so I can give the block to processor 3 and give the same block from memory. So now both processors have the block. Let's say later, processor 2 takes a write miss. Processor 2 says, I'm going to write to this block. And it's a write request to block A, or this is also called a read exclusive request. So whenever you're writing, you want to get exclusive permissions to write to that block. It sends this request to the directory. Now the directory checks, oh, processor 1 and processor 3 have this block. So I better first invalidate those caches before granting access to processor 2 to write to this block. So it sends invalidation requests to processor 1 and processor 3. And after it receives acknowledgements from them saying that they've invalidated their blocks, it sets the bits to 0. And after that, it basically takes the block from memory, sets the bit for processor 2, and makes it exclusive, saying that processor 2 is going to update this data, and sends the block to processor 2. Now processor 2 has the block, and it has it in exclusive state. And processor 2, when it receives the block, it sets the exclusive bit in the cache, knowing that the directory granted exclusive access to this block for itself. Now, there are other questions here. Do you really need the acknowledgements? Actually, you do need the acknowledgements if you want this to be a scalable system, right? Because how would the processor know that this, how would the directory know that this processor actually received the invalidation request? There's no single guarantee, single bus in this system. That's the assumption. You could have a single bus, but it doesn't make a lot of sense to have directories when you have a single bus. Okay. Okay, well, this is what I've just told you, basically. Later, let's say processor 3 takes a write miss. Let's say it's an interesting, it becomes more interesting. I'm going to delete this. Now processor 2 has a block exclusive. Processor 3 says, I want this block in exclusive state, read exclusive A. Directory receives this request. Directory sees, oh, processor 2 has the block, and it has it in exclusive state. So I'd better ask processor 2 to give me the block, because it's probably wrote to it. Right, yes? Well, it's the same thing, actually.
Oh, okay.
Yeah. So whenever I talk about read exclusive, assume that it's also a write, because it's the same thing, right? You could explicitly ask for a directory block to be read exclusive, even though you're not going to write to it, in anticipation that you're going to write to it. Right? This actually, there are instructions in some ISAs. Alpha, for example, had the write hint instruction that did exactly that. You could insert an instruction into the program that was called write hint. That would basically exactly do this: send a message to the directory saying that, oh, I'm later going to write to this block, so get me this block. It's like a prefetch from the directory, such that you don't go into those coherence overheads. Okay, read exclusive A. Processor 3 sends this request. Processor 1, directory receives it. Directory sees that processor 2 has the block in an exclusive state, which means that the memory over here probably doesn't have the correct copy. Right. So the processor directory asks processor 2 to send the cache block back to the directory. Processor 2 later does that. At that point, processor 2's bit becomes 0. Now the directory has the block. It can now supply the block to processor 3, because processor 3 actually requested a read exclusive request to it. It supplies the block. It sets processor 3's bit to 1, and it gives the block in an exclusive manner to processor 3. Make sense? Now processor 3 can do its write. And obviously processor 2's copy is invalidated when processor 2 actually receives a signal saying that, give me the block because somebody else requested it. Right. Okay, later let's say processor 2 takes a read miss. So processor 2 sends a read request to the block, to the directory. The directory sees that processor 3 has the block in exclusive state in its cache. So it sends a request to processor 3 asking, oh, give me the block. But don't invalidate it. Right? Because somebody else is reading it. Processor 3 has it in exclusive state. The directory just needs to tell processor 3, oh, give me the block, but don't invalidate it. Just make sure that it's not exclusive in your cache because somebody else is reading it. Okay? At that point, processor 3, when it receives this request, it sets its exclusive bit to 0 for that block, but it's still valid in its cache. It supplies the data because it may be modified, because it had it in exclusive state earlier. And then, when the directory receives the data, it simply sets processor 2's bit to 1, and no cache has the block exclusive. Now, both caches, processor 2's cache and processor 3's cache, has the block, have the block, but neither cache has it in the exclusive state. Make sense? So I can imagine many, many operations like this. But this is kind of beautiful because now there's someone coordinating all of these actions. And you can make it really scalable now, right? You don't need a single bus. You can add thousands of nodes to this, and they could all be communicating through the directory. Right. Okay. We'll get back to this, actually. Let's talk about Snoopy cache coherence also. The idea here is all caches snoop all other caches, read-write requests, and keep the cache block coherent. There's a single point of serialization for all of the caches. Each cache block has some coherence metadata associated with it in the tag store of each cache, as we've seen earlier. Now, this is easy to implement if all caches share a common bus, right? Because each cache now can broadcast its read-write operations on the bus, and everybody else can see it. And this is good for small-scale multiprocessors. If you have 4, 8 processors, it's good. If you start going to 16, or even 8 is tough. And we'll see that because there are several reasons, right? Single bus becomes a bottleneck because you can have only one request on the bus. You can pipeline the request, but still, logically, you have only one request at a time, at a given time. You cannot have 2 processors communicating at the same time, right? Whereas with a directory, there could be many coherence actions happening at the same time, right? And they may have nothing to do with each other. The second issue is if you have a single bus shared across all processors, now electrical loading becomes a problem, right? If you have 1,000 processors hanging off a bus, how high can you make the frequency of that bus, right? It becomes tough. So if you want to have a 1,000 node multiprocessor, this kind of Snoopy cache coherence doesn't scale. But the ideas can be at least virtually scaled. So keep this in your mind. You don't really need to have a physical bus. As long as you can, to ensure cache coherence, Snoopy cache coherence. As long as you have a virtual bus that ensures this global observation, then maybe you can still have Snoopy cache coherence. Okay. Let's first talk about a physical bus, and then we can get back to that. But basically, it looks like this. You have some processors, caches hanging off of them. Each processor is locally connected to its cache, and caches are connected to this shared bus. And there's some coherent state bits in the cache tag store. For example, MESI protocol has 2 state bits, and we'll see that. Okay, there could be, so let me actually replicate some of this over here. Maybe I'm going to use it. But the actions that I told you before are visible to caches and other processors. For example, the local processor has 2 actions that it can do on a cache block. One is processor reads, the other is processor writes. Basically, that's observed by the local cache to a block. Which one is better? The red one? Yeah. So this is cache 0. This is cache 1. Processor 0. Processor 1. And you have a bus. So this processor 0 can do processor read or processor write. And this is observed by the local cache. And the other processor can do the same thing to its own blocks. And then there's a bus read and bus write that gets broadcast to other caches on the bus. And bus write is also called bus read exclusive, just like I told you before. Okay. And we've already gone through this protocol. Basically, whenever another cache that has a block in its valid state gets a bus write for this block, it invalidates it. Basically, you broadcast not only the type of request, but you broadcast the address of the request. Bus read to A, bus read to B, for example. Which makes sense. So let's take a look at a more sophisticated protocol. The previous protocol, valid-invalid, has some downsides. But we'd like to extend the metadata to encode 3 states. You can have modified data. This is called the MSI protocol. Cache line is the only cached copy, and it's dirty. You can have shared a block in the shared state. Cache line is potentially one of several cached copies. Or you can have invalid state for the block. The block is not present in this cache. Right? This is a more sophisticated protocol that has 3 states. And this is better than this protocol because here you don't have this modified state, right? A modified state could be good because the processor can modify that cache block without informing anyone. Whereas here, whenever you want to modify that cache block, you inform everyone, right? So adding one more state, this is called the VI protocol, as I call it over here. It's not a common term. Here, whenever you want to write to the cache block, you always broadcast a bus write. Whereas if you add another state that says modified, and the semantics of the state is that cache line is the only cache copy, this is the only cache that has it, and it's dirty, then whenever you are in this state, you have a cache block in this state, and you're doing a write to it, you don't need to broadcast a bus write on the bus. Make sense? Because that's how the protocol is. So when you get a read miss, the processor makes a read request on the bus and transitions to the shared state, because some other processor may have it. When you get a write miss, this makes a read exclusive request on the bus, and the block transitions to the modified state. When a processor sees or snoops a read exclusive from another cache, it must invalidate its own copy. Right? This is what guarantees coherence, if it has the copy, of course. And if you're going from shared to modified, for example, when you're writing when you're writing to a block that's in the shared state, you just need to invalidate all of the other blocks, right? You just need to send a bus write request. You don't need to go through memory. Okay, so this is what the protocol looks like. I'm not going to go over this in detail, but you can imagine what's happening. I guess one thing that I will point out is here, if you look at this, if the block is in the modified state and the processor is reading to it or writing it, you don't need to send out any action on the bus. This is the processor's action. This is the request or action that's sent out on the bus. This is the benefit of the modified state. You don't need to send out a request. This is kind of exclusive, right? If you can think about it. Except we're going to have a different meaning, meaning for exclusive. Modified means the data is dirty. But there's a problem with not having another state. There's no state over here that says the data is clean, but I have exclusive access. Right? This state says the data is dirty, and I have exclusive access. If a cache has this block in modified state, the data is dirty, and I have exclusive access. And I'm going to show you the benefit of having a state that says the data is clean, and I have exclusive access. Okay, you can study the state diagram, and you're going to study the more complicated state diagram when you implement it. But the problem here is, if a block is in no cache to begin with, assume that, on a read, the block immediately goes to the shared state. So if you look at this, let's say the processor doesn't have the block. It basically does a read. It broadcasts a bus read to everyone. And the memory supplies the data, and it goes into the shared state, even though no other cache may have the data. Right? Shared state means that the block is in the cache, it's not dirty, but it's potentially shared by some other processor. Potentially some other cache has it. Now there's a problem with this. It goes into the shared state, although it may be the only copy that's cached, right? Only processor that caches this. And no other processor will cache it, perhaps. So why is this a problem? Suppose the cache that read the block wants to write to it at some point. Now it needs to broadcast and invalidate, even though it has the only cached copy. But it doesn't know that it has the only cached copy, because it's got the block in the shared state, and shared state says some other cache may have this block. So it has to broadcast as invalidate. And this consumes bus bandwidth, right? If the cache knew it had the only cached copy in the system, it could have written to the block without notifying any other cache. This is like the exclusive bit that we had earlier with the directory-based scheme. This MSI protocol doesn't have that because it doesn't have that state. This would save unnecessary broadcasts of invalidations, right? Especially for blocks that are never shared by some other processor when this processor is going to write to it. That's the idea. So the solution is really a MESI protocol. You add another state indicating that this is the only cached copy and it's clean. It's called the exclusive state. And the block is placed into the exclusive state if, for example, you're reading the block, you have a bus read signal going out, and no other cache has it. Make sense? So there's a bus read signal that's going out from some processor, and all of the other caches check if they have the data. If no one has the data, then memory supplies the data, and the logic over here says that, oh, you can have this in exclusive state because no other cache has the data. Of course, you need to have some logic that actually figures that out, right? If you have a wired OR, for example, that's a shared signal, that's a wired OR, can determine this. The snooping caches, the caches that see this bus read request to A, can basically assert this wired OR, if you will. And if any cache actually says, oh, I have this block A in my tag store that's valid, then what happens is you get the cache block in the shared state. If no cache asserts it, then this cache gets the cache block in the exclusive state. That's how you determine. So there's additional complexity over here. But the benefit is you save these additional invalidates. Now, when you write to a cache block, you can silently transition from exclusive to modified, because you know that it's an exclusive state, the cache has the only copy. You don't need to do invalidation. This is also called the Illinois protocol, and this paper beautifully describes it actually. It's called the Illinois protocol because it was developed by University of Illinois by Janak Patel and one of his students. So I would definitely recommend you to read this paper. It's a beautiful illustration of how this works. You don't need to read the evaluation part. The part that describes the protocol is beautiful. Okay, so what's the protocol? I've given you all of this. I'll give you the state diagram. Obviously, I'm not going to go over all of the state diagram. But we have these actions, processor read and processor write, coming from the processor to its local cache. And we have these actions on the bus read and bus write for a block. And bus write can be bus invalidate. There are two things, bus invalidate and bus read invalidate. And I'll let you think about these. Bus invalidate means invalidate but already have the data, so do not supply it. Bus read invalidate means invalidate but also need the data, so supply it. And we're going to say, you can see it in the next slide over here. So if you look at this is a state diagram. And this kind of a state diagram that you're going to implement. You have 4 states. One is invalid. We've seen this before. The other is shared clean. You've seen this before. This is S and I in the MSI protocol. And the other is exclusive and modified. This is M in the MSI protocol. So we have the state exclusive and clean. And I'll show you 2 things. One is, let's say this processor has the block in invalid state, and it does a processor read to this block. If this is the only processor that has, or that's requesting the block, no other cache actually has this block at this point in time, after this broadcast of the processor read, after this broadcast of the bus read, it goes into this exclusive clean state. Otherwise, it goes to this shared clean state. You send a processor read, this gets broadcast out to the bus as a bus read, and some other processor says, oh, I have the block, so you go into the shared state. So that's the difference. And once you're in this state, if you actually acquire the block in exclusive clean state, you can write to it without notifying anyone. This is processor write to the block, no one else is notified. Nothing gets broadcast on the bus. Okay? And once you're in this state, if you're in exclusive modified state, you can do processor read and processor write without notifying anyone. Okay, so this is another example of this. This is actually from one of the readings that I recommend. But I'd encourage you to study this diagram. In fact, you'll have to study it for Lab 7. Okay, and this is actually the state machine from Lab 7. if you look at it. This has some explanation, and we're going to put out Lab 7 soon. There's several things that I will point out here. One is the terminology of downgrade and upgrade. Basically, downgrade means you're transitioning from a state where you have more power on the block to a state where you have less power on the block, the way I like to think about it. Or, in other words, you're transitioning from the single owner state, you're the only one who owns the block, exclusive or modified, to a shared state. This is called a downgrade because the transition takes away the owner's right to modify the data. There's also upgrade, which is transition from the shared state to a single owner state. Shared state to exclusive or modified state. This is called an upgrade because the transition grants the ability to the owner to modify the data, right, to write to the block. So you can see the downgrades and upgrades over here. This is a simplified form of the diagram, and this is a more complicated form of the diagram, I think. So I'll let you study it. But this is actually implemented in real machines too. Most of the modern processors have a version of this protocol. And the Pentium Pro was a bus-based multiprocessor, and it had this protocol, basically. It exactly had these states: modified, exclusive clean, invalid, shared clean. And if you were in the invalid state and if you got a processor read, you broadcast a bus read, and there was a signal that determined whether any cache had it or no cache had it. And then based on that, you would transition to shared clean or exclusive clean. So what you're going to be implementing in Lab 7 is very similar to what Pentium Pro had in its coherence protocol. But maybe later you can compare it to Pentium Pro's protocol. Okay, so there are a bunch of trade-offs that I would like to try to cover in the remaining 10 minutes. And actually, modern processors have even more complicated protocols, and they keep adding states. But we're going to look at the trade-offs. One question is, whenever you get a downgrade from M, should you go to state shared or should you invalidate the block? Right? Well, if the data is likely to be reused before it's written to by another processor, you might want to go to shared, right? If the data is likely not to be not reused before it's written by another processor, maybe you want to go to invalid state, right? Because you have this data in modified state in your cache, and somebody else is requesting this data, and you could go into shared state, meaning that you supply the data to the other processor, and both of the processors have the data. If this processor is going to reuse the data before any other processor is going to write to it, this makes sense, right? Because the data remains in this cache. But if this processor is not going to reuse the data before some other processor writes to that location, then it makes sense to actually invalidate this, right? Instead of going from modified to shared, you may want to say, oh, I'm going to invalidate this block because some other processor is going to perhaps write to this block later on. Right? So it's all about reuse of data. The other trade-off is cache-to-cache transfer. Do you actually do cache-to-cache transfers? On a bus read, when you receive a bus read, should the data come from another cache or should it come from memory? And there's flexibility on this. If it comes from another cache, it may be faster, especially if memory is slow or highly contended. Right? If another cache obviously has this data. Whereas if it always comes from memory, it's simpler. There's no need to wait to see if another cache has the data and access that cache and get the data. Although this is probably faster because the cache is probably faster. This leads to less contention at the other caches. And if the data always comes from memory, it requires write back on M downgrade. Right? Whenever you go from M state to S or I, you need to write back the data. We're going to see this soon, actually. Actually, let me see it. Well, let me introduce the problem with the MESI also. There's a problem with MESI as well, which is the shared state requires the data to be clean in this case, which leads to one problem, right? All caches that have the block have the up-to-date copy, and so does the memory. That's what clean means. Right? It's clean. All caches, none of the caches have modified the data, so everything is consistent with memory. Now this is a problem because you need to write the block to memory when you get a bus read, and when the block is in modified state. Right. Does that make sense? If you don't do what I described earlier over here, that complicates things a little bit, but that's the idea. Basically, you don't you need to write the block to memory, which means, why is this a problem? Memory can be updated unnecessarily. So consider the case where some other processor wants to write to the block again. Right? Then you keep writing the block to memory unnecessarily. Right? So the problem happens this way. Let's say this. I should figure out which ones to use. I'm going to throw these away later on. Okay, that's better. Finally, useless copies. You have the block in modified state, and some other processor is doing a bus read. Now, because this is it's basically broadcast a bus read, and you have the block in memory, but this is not stale. This is a stale copy. This is in modified state. Now, when some other processor does a bus read, you would like to transition to the shared state, right? And how do you do that? Well, if you would like to transition to the shared state, what you do is this becomes shared, and the data is supplied from this cache to this cache. And now these are in shared state, but shared state means it's clean, right? It cannot be dirty. That means that this block, when it's also supplied, when it's supplied to this cache, has to be supplied to memory also, such that the memory is up to date. Otherwise, the semantics of shared state will be violated, right? Otherwise, shared state is not clean anymore. Make sense? So we would like to get rid of this update. If you want to improve upon this, there could be many things you could do actually. One idea is do not transition from M to S, as we've discussed, on a bus read. Invalidate the copy and supply the modified block to the requesting processor directly without updating memory. Basically, instead of doing this, instead of initially you have the block invalid over here, when this processor sends a bus read, do not go from M to S. Invalidate this copy, send the block to this cache. Now this block goes to M. Right? Now you still have, oh, it's not clean, obviously, it's dirty. You still have the block dirty, it's the only copy in the system, and it's modified. Make sense? This is a version of MESI protocol, but it's a little bit more complicated. The second idea is, now the downside of this we've seen already. If you don't modify, if you don't go to the shared state, if you're going to read it again, well, too bad. You want to get the data again. And you'll do the same thing. You keep doing the same thing between the different processors when you do ping pong. So this may be a bad idea. The second idea, which many processors today implement, is you actually go from M to S. You were in M. This was invalid. This sent a bus read. You go to shared state, but designate one cache as the owner. And this goes to shared state. But now shared state can be dirty also. And one state is designated as the owner, and the owner will write the block back when it's evicted. Make sense? So all of the caches may actually have the block as dirty, but one of them will write it back. Now shared means shared and potentially dirty. It's not shared and clean anymore. It is shared and potentially dirty. And this is a version of the Moisey protocol. This way you don't keep updating memory. Okay? So you can actually keep adding more states. If I'd encourage you to study this, because this takes some time to think about it actually. Cache coherence can get even more complicated. So you're seeing the trade-off, right? We've started with this VI protocol, and then we went into MSI, and then we went to MESI, and then we're talking about Moisey now, even though I didn't give you the state diagram. Basically, the protocol can be optimized with more states and prediction mechanisms. We haven't talked about prediction mechanisms, but you could potentially decide whether you go to a shared state or invalid state based on a prediction that you do, right? That complicates the protocol because those transitions are now based on a predictor. They're not based on just the signals that you see on the bus. You could potentially do that, and it is possible to do that. The upside of complicating the protocol is now you reduce unnecessary invalidates and transfers of blocks. And that's the big goal in coherence. If you can get rid of all of these unnecessary invalidates, that's great, right? Ideally, you would like only those caches that are going to use the block to have the block. You don't want to supply the data to other caches if they're not going to use the block. Right? So that's why having a heterogeneous update versus invalidate protocol is a good idea based on prediction. But that complicates things. However, as you add more states and optimizations, now you're complicating the system. They're more difficult to design and verify. It leads to more cases that to take care of. In fact, it leads to a lot of race conditions. You really need to get this correct. So for example, while this is happening, you cannot supply the data to some other processor. There are a lot of race conditions that need to be obeyed when you have a state machine like the ones that I described. I'm not going to go into that, but coherence protocols are one of the complicated parts of the machine to design today. And the second thing is these actually provide diminishing returns as you keep adding to these states. It's not always the case, but usually the next optimization gives you a diminishing return. Okay, I guess let me cover this and then we'll conclude. Basically, we talked about these two different coherence methods. Let's look at the trade-offs between them. Snoopy cache, it's simple, right? You have a bus. The upside is the miss latency is short. You don't need to refer to a directory, right? There's just one bus transaction. There's no indirection. So miss latency is relatively short compared to the directory. Whereas with directory, you first need to go to the directory, and the directory needs to respond. The directory needs to get acknowledgements from different processors, and after that, it responds with the data. So the latency is short with the Snoopy cache protocol. Global serialization is easy in this kind of protocol because you have a single global bus, right? Bus already provides this. Whereas it's harder with the directory protocol. It's simple because you can adapt bus-based unit processors easily to this. The downside of the Snoopy cache is it relies on broadcast messages to be seen by all caches in the same order. Well, that's the definition of a bus also, right? These broadcast messages are not really necessary because directory-based protocols require only those messages to be seen by the caches that have the block, right? That's it. That's the optimization of the directory protocols. It doesn't broadcast the messages to everyone in the system. So as a result of this, you have a single point of serialization, which is bus, which is not scalable as we discussed. You really actually need a virtual bus or some totally ordered interconnect. We'll kind of, we won't talk about virtual buses, but you can actually have some other interconnect, but have really efficient broadcasts on that interconnect that satisfies this protocol. Directory-based protocol, the downside is it adds indirection to the miss latency. You don't just go through the bus to get the data, but you actually go through the directory. There's a middleman in between the processor and the memory, right? It requires extra storage space to track share sets. Basically, directory needs to be stored somewhere. Here, you still need extra storage, obviously, which is part of your cache tag store, right? But it's much smaller than the directory, because now directory, think about all possible blocks in your global memory. You need to have these bits for all possible blocks in your memory. Let's say you have 10,000 processors. Well, maybe 65,000 processors, let's say. You have 16 bits in that case, right? Is that true? No. Well, if you do it with a bit vector, you need to have 65,000 bits, right? Per block. That's a lot, right? Or 64K, let's say. Right? That's a lot of bits per block. You can actually calculate. There's a question in one of the past midterms and finals that asks you to calculate the size of the directory. It could be huge. Because you're doing this per cache block. Imagine your memory is 1 terabyte, your cache block is 64 bytes, and you have 64,000 processors. What is the size of your directory? That's a great exam question, right? It's huge. That's the big downside of it. That's why people have developed optimizations to approximately track the share sets. As long as you maintain correctness, for example, you could use Bloom filters that we've discussed, right? As long as you maintain correctness, you can reduce the size of the directory by doing partial broadcasts, right? Instead of doing point-to-point invalidations. That's the idea. Basically, false positives are okay, false negatives are bad. You want to send invalidation requests to a superset of the caches that potentially contain that block, not a subset. Well, there's one downside, another downside. Protocols and race conditions are more complex, especially for high performance, and we will see that when we cover a little bit more detailed things in the next lecture. The big upside of the directory is it doesn't require broadcast to all caches, because it can do this negotiation between the caches on a per block basis. You don't need to, because it knows exactly which blocks is located in which other caches, right? The problem with this is you don't know which caches actually have which block. That's why you broadcast to everyone. Here you don't broadcast to all caches. And the second big upside is it's as scalable as the interconnect and the directory storage. Right? It doesn't require this single point of serialization. It's much more scalable than a bus. So you can actually have, as I said, your memory distributed across many nodes and your directory distributed across many nodes, right? And you can have many different directory requests going on at the same time. Whereas a bus, you can have only one request that's happening at the same time. Okay, any burning questions? No? I think this is a good place to stop then, and then we'll revisit some of this for a very short time. But hopefully you'll enjoy doing Lab 7.